In the last video, we introduced aldol reactions by going through the mechanism for these reactions involving two units of aldehyde or ketone that were identical to one another reacting with each other. We are going to continue this theme of aldol reactions in this video by looking at intramolecular reactions and so-called crossed reactions. When we say the term intramolecular reaction here, what we are referring to are structures where rather than the two aldehyde or ketone groups required for the reaction being provided as two separate molecules, instead we have a reaction that involves one molecule that has two aldehyde and or ketone groups present within it. And hence, the reaction occurs within that one molecule intramolecularly to yield a ring. On the other hand, crossed reactions, our other focus of this video, are also referred to as mixed aldol reactions. And what those involve are two different non-identical aldehydes or ketones reacting with one another. And so we are going to go through an example of each of these unique scenarios applied toward aldol reactions, illustrating how the mechanism for these reactions is entirely analogous to what we learned in the last video for our standard intermolecular aldol reaction with two identical aldehydes or ketones reacting. So by looking at the intramolecular aldol reaction. In the intramolecular aldol reaction, we're going to start with our starting material, our starting organic molecule has to have two aldehyde and or ketone groups in it. And this reaction is going to be most effective if the reaction of those two aldehyde or ketone groups, if it yields a 5 or 6 membered ring. The reason why yielding a 5 or 6 atom ring is most favorable is because of the fact that with a 5 or 6 membered ring, we can optimize the bond angles for the sp3 carbons to be very close to the ideal 109.5 degrees. On the other hand, if we're trying to make smaller rings like a 4-membered cyclic molecule, that is going to have a great deal of ring strain, and that definitely impedes the capacity of that reaction to happen intramolecularly. So these reactions are generally favorable if the product will have a 5 or 6 atom ring. So let's go ahead and take a look at this example problem, where we are going to start with a structure that we could refer to as 6-oxohexanal. So 6-oxohexanal reacted with sodium hydroxide as a base. So let's take a look at what will happen there. So drawing out my 6-oxohexanal, hexanal indicates that we have an aldehyde group here. The hexane indicates we have 6 carbons, so plug in my 6 carbons. 1, 2, 3, 4, 5, 6. And at this 6th position, we have a carbonyl group, and we have a hydrogen right there. And now with the sodium hydroxide present, our first step of the mechanism, since we have a base present, is going to be deprotonation. So I'm going to go ahead and first off label that as deprotonation. So we're going to deprotonate. And in this symmetrical molecule, which generally these will be symmetrical because otherwise you'll end up with a mixture of different possible products. If it's symmetrical, there's just going to be one place to remove a proton, because removing a proton at either position 2 here or on down the chain at position 5 would end up ultimately yielding the same product, so we don't need to show both. We react those protons with our base, which is hydroxide anion that we were given here. So hydroxide anion comes in, removes that alpha proton. That forces the carbon-hydrogen bond to break and the electrons to go onto the carbon to create a carb anion. Very analogous to what we saw in the last video with our intermolecular reactions. So now that we have done that, I'm going to go ahead and draw out my carbon chain here. Like so. At position number 2 of the chain, we'll now have a lone pair of electrons because we got rid of one of those protons. Our other product of this reaction step would be water in this acid-base reaction. Now, this intermediate would be stabilized by resonance. Be aware that the negative charge could be shared over the oxygen and the carbon where it's shown there, so there would be resonance. So I'm just going to list this as being resonance stabilized and assume that you can draw out the second resonance structure for that if need be, illustrating that the lone pair electrons come down to make a carbon-carbon double bond here, and the pi electrons come up onto the oxygen. So what now? Well, now at this point, we've set this up so that we have a nucleophile, our nucleophilic carbon right here, present in the same molecule as our electrophilic carbon over here. And those two can react intramolecularly. That's why we call this an intramolecular aldol reaction. So what we can show is that the nucleophile, the source of the electrons, comes over, it attacks the carbonyl over here intramolecularly. The pi electrons come up onto the oxygen like so, and that's going to lead us to our next intermediate. So second step of the reaction mechanism is that the nucleophilic deprotonated carbon, the nucleophilic alpha carbon, is going to attack the carbonyl group intramolecularly. So that carbonyl group's acting as the electrophile. Now we need to draw out what would result from this reaction. To keep track of who's who and what we need to bond where, I always like to number these atoms. So I'm going to number 1, 2, 3, 4, 5, 6, just to keep track of where everyone is going. So in this structure, we have 5 carbons here, where carbon number 5, we're showing linking to carbon number 1. 5 joins to 1. And so what that means is we have a 5 carbon ring in total. So I'm going to go ahead and draw out that 5 carbon ring in total. So go ahead and draw out our 5 carbon atoms here. 5 carbons in our ring, like so. And I will go ahead and number those arbitrarily 1 through 5. You can number these however you want. What's going to matter is what you decorate each of those carbon atoms with. We know it's a 5 carbon ring because we had 5 carbons in our chain here. We linked carbon 5 back to carbon 1, and so that would hence be a 5 carbon ring of carbons 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So at position number 1, we are going to have our hydrogen bonded there. Boom. We would also have a single bond to an oxygen, and that oxygen has 3 sets of lone pair electrons, like so. Because we took the pi bond, we moved it up onto the oxygen, like shown. The new bond is between carbons 1 and 5. I will highlight that in purple here to illustrate that that's our new bond that we made. That's what we made with our electron pushing arrow here that I've highlighted in purple as well. So that is our new bond. And we got to fill in every position here. So at position 1, we had a hydrogen and a single bond to oxygen. Position 2, CH2. Position 3, CH2. Position 4, CH2. Then we come to position 5. And we have to ask what is bonded there. So at position 5, we're now directly linked to position 1. We've already shown that. At position 5, we also have a hydrogen, which is implied, but I'll go ahead and draw it in anyway since we did it the previous step. And we also have, coming off of that, we have carbon number 6, which is a carbonyl bonded to bonded to a hydrogen. So carbonyl bonded to hydrogen here. So go ahead and show that by drawing it out. And that would correspond to, we have a carbonyl here of our aldehyde group, like so. So now we have come to the point where, to finish this off, all we need to do is grab a proton for this oxygen anion so that we ultimately create a final organic product that is carrying no formal charges. So step 3 would be protonation, which will illustrate to us that the base acts as a catalyst in this reaction because we use it up at the first step here, and then now we're going to regenerate it here at this last step by bringing in water, H2O. We take the lone pair electrons from the oxygen, bring those down and grab that proton. That forces HO bond to break. And this is going to create for us our 5-membered ring We have our carbonyl group directly bonded and hydrogen, and we have our OH group here of that hydroxy. Our other product of this reaction would be the hydroxide anion, illustrating that we're reforming that hydroxide anion catalyst. So we've created now our final product of this particular reaction, which I will circle. And this is what the final product would be if we were doing the reaction at a relatively low temperature. And we used in the last video the cutoff of, we said 100 degrees or more was kind of the cutoff, where if we're below 100 degrees, this is going to be the final product of the reaction, is the one that I'm moving around right here. And if the temperature is greater than 100 degrees, that's enough energy to provide as a next step. It's going to be enough energy to give us a dehydration reaction. So let's show what could happen next. And that is if the temperature is greater than, or we can say greater than or equal to be precise there, 100 degrees, what's going to happen is that the base will come in. We still have a relatively acidic alpha position proton there. We have our hydroxy group at the beta position. And what will happen is that the lone pair electrons in the hydroxy group come in, grab a proton from the acid. That forces the carbon-hydrogen bond to break. The electrons come down to make a carbon-carbon bond, and off comes the hydroxy group to give us a dehydration reaction. So this is what we refer to in our mechanism as dehydration. You could think of this as an E2 reaction, elimination reaction, in that the base comes in and grabs a proton from the acid at the same time as a leaving group is leaving to give an alkene product there. And the alkene product will always be conjugated with the carbonyl group. So we're going to end up with a conjugated product. And that's a good way to tell whether you're on track or not with the product that you've drawn, is it should definitely, for any of these reactions that yield an alkene group, the alkene group is going to be conjugated to our carbonyl group. So drawing out everything here, carbonyl group there, hydroxy group is left, so it is no longer in the building. Our final product is going to be what I've highlighted here. And the conjugated group of that we can illustrate as this continuous sp2 network that I've highlighted in yellow in our final product here. So as you're doing these types of reactions, you have to be mindful about what conditions they're run under, because if you keep the temperature relatively low, it's going to stall right here. On the other hand, if you heat it up to greater than 100 degrees, this dehydration reaction is going to go on. And actually, this conjugated product is so stable that we don't actually need to draw this now as an equilibrium arrow anymore, because this reaction is generally not going to be in equilibrium at this point. Instead, it's going to be a reaction that goes entirely irreversibly toward the side of the product, because the final conjugated product is so stable relative to the reactant. So this is a beta elimination, meaning that we're eliminating this hydroxy group from the beta position by reacting at the alpha position with our base, which removes a proton, forcing the formation of that alkene group as the leaving group leaves. Now, I promised you that in this video we would not only focus on the intramolecular aldol reactions, which we just did an example of, I promised we would also focus on the so-called crossed or mixed aldol reactions, which is what we are going to tackle here as our next topic, is what do we mean and how do we go about a so-called crossed or mixed aldol reaction. In a crossed or mixed aldol reaction, what we will observe is that there are two different aldehydes or ketones reacting with one another. And this particular reaction generally works best if only one of the reactants actually has alpha protons, because otherwise you often will end up in a situation where there's going to be a competition between different alpha positions getting deprotonated, and as a result, multiple products can end up forming. So this reaction, as a result, is best if only one of the reactants actually has alpha protons, and the other reactant is fully substituted at the alpha position so that there are no protons there to actually be removed. It also works best, as well if the reactant without the alpha proton is the more electrophilic carbonyl. So we'll explain as we go through the mechanism here why it is the case that this is going to work best if the reactant that does not have any alpha protons is also the one that has the more electrophilic carbonyl. These are ways that will help steer the reaction toward a single major product rather than toward multiple products. So let's take a look at an example here. We're going to go ahead and do this reaction with acetaldehyde, which is our 2-carbon aldehyde, like so, reacted with formaldehyde, a 1-carbon aldehyde. So we're going to react these two in the presence of base, sodium hydroxide, and we're going to sort out what will happen here in this mixed aldol reaction. So when we have the base present here, it's important from the get-go that only one of these two structures has an alpha proton present. In this case, it's going to be our acetaldehyde, because if there were multiple alpha protons present, the sodium hydroxide could technically be grabbing from multiple different reactants and hence creating a bunch of different carbon nucleophiles or enolates, and hence ultimately leading to a lot of different reaction products from these reactions. So in this case, we're all set because in our mixed aldol reaction, we have just one type of alpha proton. It's right here. So let's go ahead and show what's going to happen at that alpha proton when we bring in our base. When we bring in our base, we will have our CH3 here. So I'm going to draw that as CH2 and then one of my bonds to hydrogen explicitly shown so that I can illustrate that the hydroxide anion will come in. It will steal that proton in this equilibrium reaction. That forces the carbon-hydrogen bond to break and the electrons to go onto the carbon to create our enolate intermediate. So our product of this step, step 1, is going to be that the water forms and we create our enolate intermediate, H2C, lone pair electrons on that carbon, hence a negative formal charge, and it's adjacent to that carbonyl group. So step 1 here of our mechanism, same as what we've seen before, which is deprotonate the alpha position. So step 1, deprotonate alpha hydrogen. As usual, this alpha position would be stabilized by resonance, so we could draw a second resonance structure here. We don't necessarily have to for what we're trying to illustrate here. And then now that we have created that nucleophile, our nucleophilic carbon right here highlighted in green, that nucleophilic carbon is looking to react with an electrophilic carbonyl. So it looks around the reaction flask and it's going, okay, I need an electrophile to react with. And the stronger the electrophile, the more drawn this carb anion is going to be. And so as we look in the reaction flask, when we imagine we have 1 million molecules of acetaldehyde and 1 million of the formaldehyde, the one of those two that this carb anion is going to be preferentially drawn to is going to be whichever one of these carbonyl groups is more electrophilic. So of the two, the more electrophilic one is going to be formaldehyde. The reason why this carbonyl is more electrophilic is because we think of electrophilicity as being how positively polarized is this carbon. This carbon is going to be positively polarized because of the fact that by resonance we can move the pi electrons up onto the oxygen and put a formal charge there on the carbon. The other way that this is going to be electrophilic is if we have electron withdrawing groups attached here and here. And in the case of formaldehyde, formaldehyde is more electrophilic than acetaldehyde because of the fact that the two hydrogens are electron withdrawing, so they're pulling electron density away from the carbonyl and hence making that carbonyl positively polarized. Whereas over here, instead of a hydrogen on the left side, we have a methyl group, which is electron donating by induction. So it's going to be trying to push electron density toward that carbonyl carbon, making that carbonyl carbon less electrophilic. And so we're set up here as the ideal case scenario for a mixed aldol reaction because in the reaction, we've set it up so that only one of the reactants has alpha hydrogens, That is the reactant on the left here, our acetaldehyde, and only one of our reactants has a more electrophilic carbonyl. There's a difference in the electrophilicity between the carbonyl groups, with the one over here being more electrophilic. So we really need one of the structures being more easily deprotonated and the other one having a more electrophilic carbonyl. Otherwise, you're going to end up with a mix and match of different carbon nucleophiles that have been deprotonated reacting with different carbon electrophiles within that reaction mixture. So we're trying to make this not random, in other words, by strategically designing it so that only one of our reactants has alpha protons and only the other reactant has a more electrophilic carbonyl group. And so it works out here in this particular example. So now, keeping in mind that at step 2, what happens in our general paradigm of aldol reactions is that the nucleophilic alpha carbon, that carb anion, attacks and forms a bond with the electrophilic carbonyl. It's going to prefer the most electrophilic carbonyl that's present in the reaction mixture, so it's going to attack the formaldehyde. So I draw in my formaldehyde like so, and I will have my carbonyl group that is electrophilic be attacked by the nucleophilic carbon up here. So our alpha carbon is our nucleophile, comes down, attacks the electrophilic carbonyl. That forces the carbon-oxygen pi bond to go up onto the oxygen, hence giving us a new carbon-carbon bond that we're illustrating in red here. Let's go ahead and draw out the product of that step. So we have our proton carbonyl group. We have our CH2 group right here, which corresponds to the CH2 group that was in green up top. I'm going to put that carbon in green down here as well. We have a new bond, which I will show in red, that matches the color of the electron pushing arrows that we used here. And that connects to the carbonyl group here. And the carbonyl group is no longer carbonyl because the electrons from that pi bond went up onto the oxygen. So now we have, at this position, CH2, and then we have a direct bond to an oxygen, which is an oxygen anion technically, because we took the pi electrons, we moved those up onto the oxygen, giving that a negative charge. And now, as is customary here, we have a molecule that we can recognize as being an appropriate type of functional group for aldol reactions, because we have alpha, and then at the beta position is where we have our oxygen anion that's going to become an OH group. So that's why we call this a beta hydroxy aldehyde or ketone, is that what will be the hydroxy group is going to be beta to where the carbonyl group was. So let's go ahead and finish this up. So in finishing this up, our third step here of the mechanism is that we will do a protonation. And we have water present in the reaction mixture, so we could use that as our acid here. So our oxygen ion, very eager to grab a proton from any acid it can find. Water is a strong enough acid. And we will break that oxygen-hydrogen bond right here to give us our final product, OH there, CH2, CH2, carbonyl, and our final product being this structure that I have drawn here. Always a good idea to double check that your molecular logic makes sense. And in these reactions, we should always have our alpha position directly adjacent to the carbonyl. And then at the beta position is where we create that bond to the hydroxy group. And we could additionally, this reaction scenario I've shown here is what would happen if we were at less than 100 degrees. If we say the temperature is hotter than that, we would get an elimination reaction using the mechanistic arrows that we looked at previously. That's going to result in loss of the hydroxy leaving group, and we would place a carbon-carbon double bond there. So the leaving group would leave, and a double bond ends up coming in right here to give this conjugated final product. So that's a way to tell if you are creating this alkene in the product, it should always be conjugated to the carbonyl group. That's a pro tip for making sure that you are relatively on track with this and not completely out in left field. So this is our example of a crossed or mixed aldol reaction. When you're doing these reactions, you do have to be mindful when you're looking at the reactants. you have to ask yourself, is there more than one alpha proton that could be removed? If so, you've got to remove from those different asymmetrical positions. And then you also have to ask yourself, is there a difference in electrophilicity between the carbonyl groups of the two structures that are reacting? Because if there isn't, then you would also have multiple places where the nucleophile could come in and attack different carbonyl groups of different molecules. So this one can get a little dicey in that you have to be very careful to lay it out carefully, or you will end up with multiple possible products of these reactions. And there are an example problem or two in the textbook where it asks you to take a couple of different aldol reactants and show all the different products that could result from that. So you do have the opportunity to get some experience at highlighting how this reaction can get pretty convoluted pretty fast when you have multiple alpha positions that have protons and or multiple positions that are equally electrophilic. So with that, we will conclude our discussion of aldol reactions. In the upcoming videos, what we're going to do is continue looking at reactions that involve this alpha position being deprotonated, and we're going to transition into doing that for ester molecules, because esters can also be deprotonated at the alpha position in order to yield nucleophiles that can then undergo additional reactions.